Okay, so because we kind of have a mixed audience, I wanted to take a step back and talk about the lunar cratering chronology sort of as a general thing to give everybody a little bit of background. And to talk about, well, first quickly, what is it? Why is it important? And then how can we improve it? Okay, so some of you know, but I want to give you a few details about this, that we're using craters as a clock to measure time. And it's based on the observation and sort of the logic that the number of superimposed craters on a surface is related to geologic time. Okay, so when we get into actually generating a data set, what we do is we measure a size frequency distribution, and this is just one of the standard ways of plotting it, where you have a cumulative crater frequency, so the number of craters in particular size bins versus that crater diameter at the bottom. And the older surfaces have a curve that's higher, vertically higher, and the younger surfaces have a curve that's vertically lower. Okay, so that's nice, but how can we represent this in a way that it's easier to communicate this relative age difference? Well, we first have to standardize these curves. So we use a lunar production function. That's the size frequency of craters forming on the lunar surface as a standard shape that these curves should follow. And we can move that up and down to give us a reference and make sure that those crater size frequency distributions that we measured are consistent with each other. Okay, and then if we want to take one number that we can use to compare between these relatively aged surfaces, we can just define a reference value. For example, often is used N(1), which is all the craters, the cumulative number of craters larger than 1 kilometer in diameter, although you see this also N(20) and more than that. Okay, and so then how does that combine? If you take your N(1) value that you measured with crater size frequency distribution, how do we combine that then to get an absolute age of a surface? Well, it has to be calibrated against the lunar samples. And this is where we all have to work together to get the best data possible on both of the axes of what's going to be the lunar cratering chronology. And so basically here we take the sample ages, and there we need to have discussions about which sample age actually represents this Mare deposit, this Mare basalt deposit, the example here for the Apollo 12. And so we combine the N(1) that's taken from the surface with the sample ages. We do this for all of the lunar samples that we have and come up with a data set that looks like this. So we have the absolute age from the samples, or the radiometric age, or radioisotopic age on the bottom versus this N(1) that I described. And then this figure will look familiar because Wajia also showed it. Then you can fit this data set with different kinds of chronology functions. And so the goal is to be able to, anywhere on the surface of the moon, figure out what the N(1) is based on the crater size frequency distribution, and to then solve for an absolute age for that unit. So why do we want to do this? Why is it important? Because we want to have some tools that give us a geologic framework for interpreting the geologic evolution and history of the moon first. And then we also want to be able to apply this to compare the moon with other planets. So that's the really big picture. We can take the chronology function and apply it to other planets. And the important thing right now is that we only have samples from the moon where we know exactly where they came from. And hopefully sometime we'll have Martian samples to add to make a Martian cratering chronology. But we just have this for the moon. Let me just close this. Okay, and so I'm just going to recommend, this isn't active anymore. Yeah, okay. To go and have a look at the Hiesinger-Tanaka planetary timescale paper, because basically then you can spend a lot of time looking at the current ideas of the planetary timescales across the entire solar system. So this is the super big picture that lets us look at the evolution of the solar system over time. So how can we improve this? Well, what Gia just talked about, the part of improving the N of 1 reference values, and that involves making new updated geological maps and basically improving the count areas for the CSFD analysis. We can also refine and improve the lunar production function, which is something that our student Astrid Oetting is going to present at the poster session. And then also we can also improve the sample age part of the calibration. And then naturally we want to add new calibration points. Adding new sample ages is where now we get into the exploration part of the equation. And so prior to the Chang'e 5 mission, I helped to do a lot of work on proposing the isochron mission that would go to the P60 basalt to the south of Aristarchus, because that's one of the youngest basalts or measured with the CSFD technique. It would be great to have samples from there. And then Chang'e 5 was planned to go to the Mons Rumper region, which is slightly older than P60. And indeed, they were successful doing that. So we were able to then, with the Chang'e 5 mission, fill this gap that's in the middle between 3 and 1 billion year age. So what I did with my group in Münster was to take a look at refining work that Yuki Hyun did. He also did a geologic map to make a calibration point for the Chang'e 5 samples. And indeed, when we plot the point on the existing Neuquén chronology, you can see that it plots right there, just slightly below the Neuquén chronology function. Okay, so this is good news. And what this means when it plots slightly below that chronology function is when you're using that chronology function to determine an absolute model age, those ages are slightly underestimated, or for those locations in this flat part of the curve. Okay, and another interesting thing is I worked on refining the P60 range of ages that we would expect to see based on the statistics. And it's actually statistically distinguishable from the Chang'e 5 basalt. And so I would argue we still need to go there. We still need to get another basalt. It would be expected to be about 1 billion years younger than the Chang'e 5 basalts. Okay, so my last slide, I want to point out that it's really important to add more ages. What have we not done yet? We don't have anything up in this really old, older than Imbrium part. I mean, there's some samples that are inferred to be from Nectaris, but we don't know for sure. We need targeted missions to go and collect SPA material and maybe material from other basins that are older than Imbrium to fix that older part of the chronology function. And I would also argue that we still need to go to the P60 region to grab a basalt that is as young as possible, because all of the other materials that are younger than that are crater materials. And so that's kind of a little bit different materials. And so, yes, we need to continue to push for missions that collect the samples that will fill in the rest of this picture, and then allow all the sample scientists to do some great work in the lab. So thank you.